All right. Good morning, everyone. Welcome to CS 5210, Linear Programming and Combinatorial Optimization. This is the first offering of the course, and today is the very first lecture. Okay. We are recording now, and after the lecture, the video will be available on YouTube on my channel. Okay. So I'll share a screen and we can discuss some administrative and logistical matters regarding the course. And then if time permits, we can actually get started on some material. And between the two, we will take some questions. If anybody has any concerns, those can be addressed too. Okay. All right. So I'm sharing a screen now. Is it visible?
Yes.
Yes,
Okay,
sir.
great. Thank you. Thanks. All right. So let's just discuss administrative and logistical matters and get them out of the way. Um, so the course has a web page, which is in the WhatsApp group, in case you're already on the WhatsApp group for the course. If not, then you can just Google my name and you will find my web page and you can find the course web page in there. Okay. We are going to be using, maybe I don't want to use red color. Let me switch to black. Okay. So we'll be using several different portals and platforms for discussions. So the main one is Piazza. In case you don't have an account, please open one. And if you are already registered, you should have received an invitation. So please get used to it. I strongly recommend using Piazza for almost everything, especially discussions pertaining to the course, because Piazza allows LaTeX math code with between $2 signs. You can put any math code you like. Okay. And we will also be doing assignment, release, and submissions using Piazza. Okay. And it's a pretty easy interface, so I hope you can get used to it soon. Apart from Piazza, we have a WhatsApp group for the course for anyone who is auditing or crediting the course. Auditing is a completely informal thing. There is no formal concept of auditing at IIT Madras, as you may already know. So that means that if you audit the course, it does not appear on your transcripts or anything, right? It's just something you do from your own volition because you're interested in the material. Okay. There is also a YouTube channel. You can check that out. It's easily available if you just search my name with IIT Madras, and all the lectures will be put there. Okay. And we are using Google Meet as we are already using right now for all the lectures. And the link has been sent to you. If you are using a different account to enter the meetings, please let me know so that I can enter that email address and I don't always have to admit you into the meeting because you're using a different account. Okay, so that will save me some time and trouble as well. Okay, but I recommend using the SMail account if you can. Okay. Good. So those are the things we are going to be using for the course. Are there any questions or concerns? Okay. If not, then let's see. So let's look at the course structure. So this is tentative. The beginning, most of the part is kind of fixed, but the last parts, there might be some small changes because this is the first offering of the course. So we might make some minor changes towards the end. So I like to break a course into modules just so that there is some structure to it, right? So I'm calling this first module Preliminaries. Why not? And then we will be looking at geometry of linear programs and the simplex method. And then we'll be looking at duality, linear programming duality. And finally, one of the most important modules is primal dual algorithms, where we'll be using linear programming and linear programming duality in order to solve combinatorial optimization problems. If you don't know what some of these terms mean, don't worry about it. I'll go into more details in the first module, which is the preliminaries. Okay. All right. And at the end of this, so this is like the core of this course. And after this, I plan to do matroids, which is one of the very important topics in combinatorial optimization. But I'm not going to set this in stone. Okay, so we will see how much time we have, and there is another topic, another few topics I have in mind. So we might make some changes towards the end of the course, depending on how much time we have left. Okay, but this is in some sense the core of the course. Okay. Good. And what are the prerequisites? Well, in the official description, I think it's CS1200, Discrete Math for Computer Science, or MA2130, which is Basic Graph Theory, offered by the Math Department. Right. But in particular, I want to mention some topics that are particularly relevant, because not all of the content in these courses is relevant to us. Right? So I expect basic linear algebra. So you should know basic concepts such as what is linear independence, what is a basis, etc. Right? And you should know basic graph theory. Basically, you should know the key, let's say, I mean, it would be good to know the key terminology, but I will be defining it anyways. And it will be good to have familiarity with very basic results in graph theory. For example, a graph is bipartite if and only if it does not have an odd cycle as a subgraph. I hope most of you have seen this in your previous courses, right? So I'm just giving you an example of a result that would be good to know. Right. Okay, but anyways, we will be covering some basics of graph theory in the first module in case you don't have much familiarity. But that might mean that you have to do some extra work to cover up that basics. Okay. Good. All right. There are 2 books for the course, but you are not required to have any of these books because I am expecting that my course notes and the lectures will be sufficient to be able to complete the course and the assignments and everything. So this is the first book. It's called A Gentle Introduction to Optimization. And this is the book we'll be using for the linear programming part of the course and for some aspects of the combinatorial optimization part as well. And this is another book, Combinatorial Optimization, by 4 authors, Cook, Cunningham, Pulley-Blank, and Shriver. I'm mentioning because there are multiple books with the same name. Okay. And we will be using this for more advanced topics in combinatorial optimization. But as I said, I don't expect you to have any of these books. If you happen to have a physical copy or an online copy, feel free to refer to them. But not having them should not affect your performance. That is my hope. Okay. Are there any questions or concerns at this point? All right. If not, let's talk about some other points. Okay. So evaluations, something that you all must be curious to know about. So because this is an elective course, and because I'm not a fan of exams and quizzes and all that, the whole course evaluation is going to be based on assignments. Okay, assignments are also known as homeworks, right? So roughly you can expect there to be 5 to 7 assignments. I'm not sure of the exact number, but let's say for now we go with 6 assignments. Okay. And I will try to make it so that there is 1 assignment per module, but I'm not going to commit to it because there might be some overlap. Okay. And for each assignment, you will have 10 days to complete it, approximately. Okay. And these will be spread out throughout the semester. I'm not going to announce any specific dates right now because you have 10 days. It should be fine, right? But you can expect one assignment roughly every 2 weeks, given that we have 14 weeks in this course, roughly every 2 to 2.5 weeks, you can expect there to be one assignment. Okay. Good. What else? On assignments, you are not only allowed to, you are encouraged to collaborate. Okay, and I will explain what I mean by collaboration. So collaboration means, so these assignments are going to be very theoretical. The whole course is very theoretical, right? So mostly you are going to have proof related questions. Okay. And collaboration means that you are encouraged to discuss with your peers ideas, but not to exchange written material. Okay. So the meaning is that you may exchange ideas, but no written material, right? So for example, if you're collaborating with two others, the collaborations will be in groups of 2 or 3, or you can do individually, 1, 2, or 3 per group. And if you're collaborating with, let's say, 2 other individuals, then the 3 of you might have a meeting to discuss your ideas, right? Because everything is online, you might have a Google meeting or something, and that's fine. But any written material or any notes that you take down during this meeting, you should discard it at the end of the meeting. Okay. So collaboration should not turn into plagiarism. All right. We may have a TA. If not, I will be marking everything. Otherwise, the TA and I will be sharing the workload, and we will be looking out for plagiarism. You are required to list your collaborators in every assignment, and all the assignments need to be LaTeX. Okay. And I will give you a template. So you just need to fill out that template. You don't need to prepare your own template. And in particular, you need to list your collaborators. Okay. Failing to list collaborators or failing to put your own name down, which happens sometimes, will amount to a case of academic dishonesty. Okay. All right. Are there any questions or concerns regarding the evaluations? None? Okay. So you need to, so each person needs to submit their own responses to the assignment. Okay. So even if you're collaborating in a group, you all need to individually LaTeX your responses and submit them through Piazza. Okay. I will give out instructions on how to submit through Piazza. You basically need to create a private post and share it with me and with the TA if a TA has been allotted to the course. Okay. But do not make it publicly available. In any case, I will send instructions when the first assignment is announced. Okay. Good.
Sir, I wanted to ask
We are
something.
not planning. Yeah, go ahead.
Sir, is it
Yes.
possible to use grade scope for this, for submitting assignments?
What is grade scope?
Sir, we used it in our previous
What is grade
courses.
scope? Yeah.
So it allows us, professors, to post assignments and students to take them or fill them and submit them back. So there is no worry about making it public or anything. So we used it for
Hmm.
LARP and machine learning course last semester.
I see.
Yes, sir. So, and also the revaluation and the marking there is pretty easy because it's question wise. So it might actually even help you as an
Yes, sir.
instructor and us as the students in case you want to communicate doubts.
Okay, grade scope. All right. What I will do is I will ask my TA to explore it if we have a TA, or I will have to do it.
Yes,
So I'm not going to promise anything right now. I will look into it. I am very used to Piazza because I've been using it for the last 10 years or so. So, but in any case, if we don't use it for this course, I might explore it and might use it for the next course. Yeah. So thanks for the suggestion, and I'll definitely look into it. So how do you submit that? You submit like a PDF file?
yes, sir. So whatever LaTeX is
Yes,
there,
sir.
we can finish it. We can submit the PDF file.
I see. I see. And why is the marking any easier? So why is the marking easier in particular?
So it's like question wise. You can have a rubric for each answer. So for us, we used to know where they cut marks and why. So a diagram was missing, or a particular proof statement was missing, or there was
I
some
see.
answer was not clear.
Okay.
The TA could actually give us explanation as to why they cut the
So
marks.
yeah, I get your point. Okay. So what I have been doing, and this might be less efficient, but what I have been doing in my previous courses, I give detailed feedback for every submission. I annotate the PDF and I upload the annotated PDF on Piazza in response to the same post that was initiated by the student.
Yes, sir.
So
So
detailed feedback will
annotation.
be given.
Okay.
Right, go ahead.
I think even Gradescope allows annotation of PDF, like you can write on it or something, or you can
Okay.
type out some portion.
Okay, sure. So in any case, whether we use Gradescope or Piazza or anything else, you will get detailed feedback for all the reasons why you've lost marks. And if you don't have feedback for a particular problem, then you just need to approach us. But yeah, the idea is to give you detailed feedback for what reasons you have lost marks. We may not have rubrics because these are proof related questions, and it's very difficult to have exact rubrics for things, right? It's like an essay. If you have an essay question, you can't have an exact rubric for things, but explanation will be given for why you have lost marks. Okay, but anyways, I'll look into Gradescope, and we will see if that is a good idea to use. Yeah, is that fine?
Yes, sir. Thank you very much.
Okay, thanks. All right. Uh, okay, good. Any other comments or questions, concerns? Right. So for now, I'm just going to say that we are going to do things through Piazza, but we will look into Gradescope and see which course did it was it used for. Can you let me know? I can probably have a chat with the instructor as well.
I had it for LARP Mitesh sir,
Mitesh. Okay.
and then Ravi sir for machine learning.
Okay. Great. Okay. I'll probably have a chat with them. Thanks. All right. Good. Um, Okay, so at this point, we are not planning to have office hours. I've had it in the past, and we have seen that hardly anyone attends office hours. So, what we are going to instead do is we are going to tell you that if you would like to have a meeting, you send a message on Piazza or WhatsApp to me or to the TA, and you request for a meeting to discuss your doubts, and we will arrange a meeting for that. Okay, so feel free to approach us, and if you are able to resolve the query on Piazza itself by initiating a written discussion, then that would also be fine. But if you think that you need a meeting, then we can arrange that by one-on-one conversations. Okay. All right. Um, so I
Hi,
think
sir.
that's yeah. Go ahead.
Good afternoon. So I just wanted
Yeah.
to ask that would we be having any tutorial sessions?
No, all of the four timings in the week will be lectures. There is no plan to have any tutorial sessions.
Okay. Thank you.
Yeah, thanks. I would like the lectures to be very interactive. So whatever concerns you have, doubts you have, interrupt during the lectures and get them resolved. And if you are not able to, or let's say after the lecture you get confused about something, just initiate a discussion on Piazza, a public discussion as far as possible, so that other students can also participate and contribute to answering your questions. Okay. All right. Any other concerns, comments? All right. If not, let me just say a few words about the course objectives. All right. So, the course is linear programming, abbreviated as LP, and combinatorial optimization. These notes that I'm writing will also be made available as a PDF at the end of every lecture on Piazza. Okay. Right. So the way I see it is, we are going to motivate things using combinatorial optimization. So in some sense, the main goal is to understand, look at some combinatorial optimization problems and see how linear programming theory can be used to solve those particular combinatorial optimization problems. Okay. So that means that we will start with some combinatorial optimization and see how combinatorial optimization problems are related to linear programming. Okay. So that is what we will be doing in the very first module. And through that exercise, we will understand what linear programs are. And then from module 2 onwards, for the next 1 or 2 modules, we will study linear programs and its theory. Okay, that will include the geometry, simplex method, linear programming duality in particular. And once we have a good understanding of that, we will go back to combinatorial optimization and see how that theory that we have seen in the preceding lectures or in the preceding modules can be applied to the combinatorial optimization problems that we have in mind. Okay. And that will be the most important module, which I call the primal dual methods. Right. This one. And after that, we will go deeper into some topics in combinatorial optimization towards the end of the course. Okay. So in particular, I want to start talking about combinatorial optimization problems today, right? But we might not get to the first problem. We might just do some sort of a warm-up of graph theory in order to get to our first combinatorial optimization problem. All right. Are there any comments or any questions on these things? All right. So in that case, let me add a new page and let's start talking about basic graph theory, because the combinatorial optimization problems will be graph theoretical problems, like many of them happen to be. Okay. Good. So all right. So what is a graph? Hopefully most of you have seen graphs before. So I'm just going to draw one example. The drawing is merely a representation, and that is why I like to emphasize that a graph is an abstract mathematical object. And what I mean by abstract here is that there are many different representations. and you may have seen some of them before. The most obvious representation of a graph is a drawing, but drawings can be many, so I'm going to say drawings, like you could draw a particular graph in many different ways. And there are other representations, such as in the form of matrices. You might have seen some of these before. If not, we will talk about them when the time comes. Adjacency or incidence matrices. We will see them later. Okay. So in particular, a graph is going to have a set called the set of vertices. Often people call them nodes, but we will try to stick to vertices. Okay. So G is a graph. It's going to have V of G, the vertex set, and E of G is the edge set. So what is an edge? An edge is a subset of two vertices, of two distinct vertices in this case. Okay, so an edge is an unordered pair of distinct vertices. If you take a course on graph theory, you might see that some people allow two vertices to be joined by multiple edges, and a vertex having an edge that has, it's basically not a pair of distinct vertices, but it's the same vertex, v comma v. Okay, so we are not going to allow these in this course. When I teach graph theory, I allow these, but in this course, we are going to assume that all graphs are what are called simple graphs. Okay, so when I say graph, I mean a simple undirected graph. Okay, maybe I should say that. So we don't have any directions on the edges in case you have seen directed graphs. But if you haven't, then don't worry about it. Okay, so when I say a graph, I mean a simple undirected graph. Right? So different drawings. Let me give you one example. Here is a drawing of a graph called K4 because it's a complete graph on 4 vertices. Here, complete refers to the fact that any 2 vertices are joined by an edge. Okay, so this graph is called K4, just as an example. And you can draw it in many different ways. Here is one nice drawing of the graph that looks like a tetrahedron. Okay, the only point I'm trying to make here is that these are 2 different drawings. Right? They are the same graph, just 2 different representations of the same graph. Okay. All right. Are there any questions or concerns regarding all of this that we have discussed so far? Okay. If not, I want to mention a few other terms that will be useful in our discussion so that we are precise about things and you're not scratching your head as to what I'm talking about, right? So, all right. So some basic terminology before we can actually get started with more interesting stuff. Okay, so I won't write down definitions of terminology. I'll just give you examples because I think examples speak a lot more than verbose definitions of things. So we will say that 2 vertices are adjacent if they are joined by an edge. Okay, so in this example, 0 and 2 are adjacent vertices, whereas 1 and 3 are non-adjacent, right? Because there is no edge joining 1 and 3, or there is no edge containing which has the subset 1 comma 3, right? Okay, so since I'm saying this, if we have an edge UV, we will say that the edge E joins U and V, right? It makes sense. And we might also say that U and V are the ends of the edge E. Sometimes you will find it useful to label edges rather than just referring to them by their endpoints. Okay, so in this case, we may also write E is equal to UV. Okay, and remember that these are unordered pairs of vertices, so I can very well write it as equal to VU. Okay. All right, so that is adjacency of two vertices. In a similar sense, you can talk about two edges being adjacent, but we won't find that useful, but I just want to mention it. So in this case, you would say that 0, 2 and 2, 3 are adjacent edges because they share an endpoint, namely 2, whereas 0, 1 and 2, 3 are non-adjacent edges. Okay, good. So that is adjacency. What about a vertex and an edge? So when we are referring to a vertex and an edge, rather than using the term adjacent, we will use the term incidence. Okay, so we can say that the vertex 2 is incident with three edges, 2, 0, 2, 1, and 2, 3. Okay, so that is incidence, and until this point is adjacency, and that is where the terms adjacency and incidence matrix come from, in case you have seen them before. Okay, good. One more term that we might find useful eventually is the concept of neighbors. So if you look at the vertex 0, its neighbors are 1 and 2. That is what you would guess it should be, and that is exactly what it is, right? So the neighbors or the neighborhood of 0 in this example is equal to 1, 2. Okay, and we might write that as the neighborhood of the vertex 0, like that. That's the notation. Okay, good. All right, so I think that's basically most of the basic terminology. I do need a notation, right? So when we talked about incidence, we will use the symbol partial. So in LaTeX, this is partial. Okay. We will use partial for the edges incident with a vertex. So if I say partial of 2, I mean the three edges that are incident at this vertex, right? That will be 0, 2, 1, 2, and 2, 3. Okay. Good. So to make it very clear, partial of V is the set of edges incident with vertex V. Okay. All right. So I think this should be sufficient graph theoretical terminology for us to get started with more interesting discussions. Are there any questions or concerns regarding any of this terminology? All right.
Sir,
Yeah, go ahead. Yes.
sir, incidents you told, suppose the incident of 2 are 2, 0, 2, 1, and 2, 3,
Right.
all these edges.
Right.
And partial of vertex V is a set of edges incident with vertex V. So they
Right.
are same or
Yeah, right. That's just the terminology and the corresponding notation. You're right.
okay, okay,
Yeah, so I should have defined it back then. I forgot. Yeah,
okay, sir.
yeah, exactly. Okay. So just to see one more example, partial of 3 in this case will be simply the edge to 3. Okay. Great. All right. One more thing: if we have multiple graphs in consideration, then we might put down the particular graph we are referring to as a subscript. So, supposing we are talking about two graphs G and H, we might put the graph G as a subscript if we are referring to the graph G in the particular context. Okay. But if the graph is clear, then we won't put a subscript. And this basically goes for everything. Okay. All right. Great. So that's the very basic graph theory that we are going to need. Okay. So let's switch to a new page. So I want to start talking about a particular combinatorial optimization problem. Um, we will look at a more real world example to motivate things tomorrow. But today, given that we have only 10 minutes, I just want to get to the definitions and then look at a real world example tomorrow, right? So many of you might have seen matchings in your previous courses, especially if you have taken advanced courses in algorithms. You probably have seen matchings in your previous courses. Okay. So, but if you haven't, don't worry about it. So I'm going to start with an example. So let's consider this graph. We'll probably draw this graph many times in the course. So let me label the vertices 0, 1, 2, 3, 4, 5. Actually, you know what? Let me use V0, V1, V2, V3, V4, V5. And let me also label the edges as E0, E1, E2, E3, E4, E5, E6, E7, and E8. Okay, so we have got 6 vertices and 9 edges. Okay, and this is our graph G for the current discussion. So, we are going to define what is a matching. As I said, you might have already seen it. Does anybody want to tell what the definition of a matching is, if you have seen it before? Varun, are you familiar with the matching?
Yes, sir. We came across this, but I'm not sure about the very formal definition that I get.
Don't worry about formality. You can see how formal I am in definitions. If you know the intuitive definition, that's good enough.
I mean, it's something like the edges that do not have a common vertex. So
Good. That's
probably
all
like
it is. Yeah.
E6, E7, and E8 can be a matching.
Great. Let me put down E6, E7, and E8. Okay, that's a very nice one because it's easy to visualize. So this is a matching. It's a set of edges that do not have any vertex in common. So between any two, there is no vertex in common. In other words, any two edges are non-adjacent. Right? Can anyone give me a different matching? Sorry, Ken, I didn't hear you. Harsha? E2, E7, E5. Okay. E2, E7, E5. That is also a matching. Okay. Can someone give me a matching that is smaller? Are all matchings this big? E0, E4. E0, E4. Okay, let me put this one down. So E0, E4 is also a matching.
E1, E4.
E1, E4 is also a matching, right? Okay, so now we have a good idea of what a matching is. So let me just put down the formal definition. So a set M, which is a subset of the edge set of the graph, is a matching if, I'm going to write it in a very specific way. If you look at any vertex V, and you look at how many edges of the matching are at this vertex, incident at this vertex, then this quantity has to be, can someone tell me what this should be? For each vertex, the number of edges incident at that vertex, what should that number be? I want you to parse this notation because we'll be using this notation quite a bit. So good to get used to it from now. Okay, so if you look at any vertex and you look at the edges, the number of edges incident at that vertex from your set that you claim to be a matching, what should that number be?
So it should be 0 or 1.
1 I heard.
Zero.
What was the other number you said? 0. Exactly. Okay. And another way to say it is no two edges, or another, maybe I'll put it this way. Any two edges are pairwise non-adjacent. Well, any two, I'm already saying any two, so the any two edges are non-adjacent. Okay. So this is one way to say it. This is another way to say it, and of course there is many ways to say it. All right. Notice that these two are equivalent. All right, so that is a matching. But there is something special about the red matching. So the red matching, if you look at any vertex, you don't see 0 edges from the matching, you always see 1 edge, which means each vertex has been matched to some other vertex. In the red matching, V0 has been matched to V3 and vice versa. Right? So this is what we are going to call a perfect matching. Okay. So a set M, subset of the edge set, is a perfect matching. And because I will have to write perfect matching many times in the upcoming modules, I'm going to abbreviate it as P dot M dot. Okay. It is a perfect matching if this quantity is always equal to 1. Okay. Good. Are there any questions or concerns at this point? Okay, quick question. What about this graph? Does it have a perfect matching? No. Ravisri says no. Right. And why would that be the case? Is there a short argument for that? Okay. Well, I guess most of you can see it. You will have to match the vertex 0 to one of the three. So let's say you match it to 1, and now you basically have no choice to match 2 and 3, right? Exactly. Right. Thanks. Okay, so this graph, for example, does not have a perfect matching. What about matching? Does every graph have a matching, or can you give me a graph that has no matching? All graphs have the empty set as a matching. Yes, exactly. Thank you, Kshitij. All right. So all graphs have the empty set as a matching, right? So there's a clear difference. A graph may not have a perfect matching, but definitely any graph has a matching. Okay, good. Okay, so what I want to do next is I want us to think of a different way of thinking about matchings, and we are already at 12:50. So I will just pose the particular question I have in mind, and we will conclude the lecture at that point. Okay. So what we want to do is we want to let's call it a different viewpoint. Okay. And the idea is we want to basically get to defining or looking at an example of an integer linear program. I have not defined what an integer linear program is, but that's fine. So we want to get there by thinking of it from a different viewpoint. Okay, so let's go back to our example, the graph G. Okay, V0, V1, V2, V3, V4, V5. Okay, and we also had labeled the edges E0, E1, E2, E3, E4, E5, and E6, E7, E8. So what I want to do is I want to come up with a system of linear equations or inequalities. So what do I mean by linear equations? So something like a1x1 plus a2x2 less than equal to, let's say, some constant c. C is a constant. Right? So this is a linear inequality. Either we'll use less than equal to or greater than equal to, or we will use equal to, right? So those will be linear equations. So these are called linear constraints, and we will talk more about them rigorously later. And I want to use this idea to define a matching or to view a matching and also for a perfect matching. Okay. And the way we will do it is we will assign variables. So we will put some variables. You need to think about what are the variables and you need to think about what are the constraints. So this is a try it yourself problem. So whenever I write TIY, I mean try it yourself. And it generally means that we are going to discuss it in an upcoming lecture. Okay. So I want you to define some variables for the graph G. You need to figure out, or you need to think about what these variables are going to be. And I want you to write down some constraints. Okay, what do I mean by constraints? I mean linear inequalities and linear equations using these variables. So x here, they are the variables, and a1, a2, c, and all these are constants. Okay, so x's are the variables. And I want you to write down some constraints so that all integer solutions to these constraints correspond to matchings of your graph. And similarly for perfect matchings. Okay, so if you've already seen some of this material, you already know what I'm talking about, but some of you may not have seen it. So just think about how you would do this. Okay, so you want to put down some variables for this graph, and then you want to write down some constraints so that whenever you take an integer solution, it will correspond to a matching of the graph and vice versa. Okay, so that's the try it yourself problem, and we'll continue from here on Wednesday at 5 p.m. All right, so the lecture is officially over. Feel free to leave. I'm here for another 5-10 minutes in case there are any questions or concerns. If you want to discuss anything about whether you are planning to credit this course or audit it, or you just want to have a discussion regarding that, just stay back and I can have a chat with you. Or if you prefer, you can send me a WhatsApp message or something, and we can try to find a time to have a Google meeting and discuss matters. Okay, so I'm going to stop recording now.